Hi everyone, I'm Trang Duong. I'm in the Netherlands. My affiliation is shown here on the slide. It's my pleasure to give a talk in our workshop on intermittent estuaries in a changing climate. I would also like to thank the organizers for this great event. The title of my talk is Modeling Climate Change Impacts on Intermittently Closing Inlets. The work was done together with Professor Roshanka Ranasinghe and Professor Dano Roelvink. Intermittently closing inlets, ICIs, are the system that may be closed few times in a year. An example of the system is Maya Inlet in Sri Lanka. It's located in the southwest coast of Sri Lanka, and the inlet just closes whenever river flow is small. As can be seen from the satellite images in 2006, the system was opened in August, then it was closed in September. It's remained to be closed in October, and it reopened again in November. In this study, we focus on small tidal inlets, STIs, which are the system with the inlet width is less than 500 meters, connected to estuary lagoon with the average depth is not more than 10 meters, and the surface area is not more than 50 square kilometers. We also focus on the inlet stability in terms of cross-sectional stability and locational stability. A cross-sectionally stable inlet is an inlet that does not close in time, but it may or may not stay fixed in one location. Whereas a locationally stable inlet is the inlet that does not change its location in time, but its cross-sectional area may or may not remain constant in time. Based on the general morphodynamic behavior of this system, there are three main small tidal inlet types. Type 1, permanently open locationally stable inlets. Type 2, permanently open alongshore migrating inlets. And type 3, intermittently closing and locationally stable inlets, ICIs, that we focus on today. There's a criterion for over inlet stability, which is Bruun criterion 1978. It's the rate between tidal prism and the annual littoral transport. This is the Bruun table for the inlet stability classification. So for example, if the Bruun rate R is less than 20, then the system is classified as unstable system. There's also inlet type. So there's a question that is there a link between these two? Duong et al. 2017 extended this classification scheme to link the inlet type and the stability conditions. Also, the last unstable Bruun class is now divided into three subcategories. So for example, if the Bruun rate is in the range of 10 to 20, the system is unstable and also the migrating inlet. If the Bruun rate is from 0 to 5, then the system is intermittently closing inlet. The morphodynamic behavior of the inlet system is governed by the balance of oceanic processes, including tides, waves, and mean sea level, and the fluvial processes such as river flow. Any potential change in the system focusing may change its morphodynamic behavior and also the inlet stability condition. Under climate change, there could be change in mean sea level, river flow, and also wave conditions. This is the projections of the global mean sea level, the projections for the change in the river flow in future, as well as the projections of the change in the wave conditions, including wave direction, wave height, and the wave period. I should mention here that I cited the work of Himo et al. 2013, as it was the data available and was used at the time of this study. Recently, this work was updated in the work by Morim et al. 2019. So how to model the impacts of climate change on the ICI systems? It can be done by following the ensemble modeling framework shown here with 5 steps, and it zooms from global scale to the local scale. So from the greenhouse gas scenarios, it goes to step 2, global climate model, and dynamically downscale to step 3 regional climate model, and then to the regional coastal foxing model in step 4 to provide the input for the local scale coastal impact models in step 5. This modeling framework also accounts for the uncertainties of different future scenarios and also different models. So up in step 4, we will obtain the dynamically downscale of future system foxings, meaning the future projections of the wave condition and also river flow to use as input for the local scale coastal impact models in step 5. Next, I will show the methodology for step 5 local scale coastal impact models. In this case, here we use model Delft. So instead of long-term simulation about 50 to 100 years from present to future, we do the snapshot simulations with the simulation length of about 1 year or till inlet closure occurs. So in present we have present model PS with the present bathymetry and present foxing. PS model will be validated for the present conditions and reproduce the present observed morphodynamic behavior of the system. And with a validated PS model, it will be used for the future model CS with the future bathymetry and the future foxing for the future years, for example, at the year 2050 or 2100 to finally obtain the projection of future system behavior in terms of closed, open, locationally stable or migrating state. If we can follow this ensemble modeling framework, we consider it as data-rich environment. However, there would be cases that there's no details present bathymetry of the system. There's also no dynamically downscan of the future foxing of the system. Then we consider it as data poor environment. So the methodology for data poor environment is that we would use the schematized flatbed bathymetry instead of the real system bathymetry. Also, the future foxing will be adopted from the available global projections. As an example of the application of this approach for a case study, Maria Inlet in data-rich environment. In this case, we models the closure of Maria Inlet system. Here we have the present measure bathymetry by following the ensemble modeling framework. Upstream step 4, we obtain the dynamically downscan of the future system foxings by the year 2100. So with the future system foxing, including future river flow, projection of future wave conditions, they will be used as an input for the Delft local scale coastal impact model in step 5 with the snapshot modeling approach. So here we have present model PS and future model CS. This shows the Delft model results for the present model PS on the top and also future model CS at the bottom. The future model CS was done for the future year 2100 with consider the change in the wave conditions and also river flow and also takes into account the sea level rise. As can be seen from the top figures of the present model, it takes about 45 days till inlet was totally closed, whereas in the future model, with the future foxing, inlet remains to be open for longer, and only after 78 days inlet was closed. Looking at the Bruin stability criterion for inlet stability, in the present model, the Bruin rate equals 1, and it increases to 5 in the futures model. So as can be seen that, but at both present and future models, the Brunt rate is seen in the range from 0 to 5, and the system remains as the intermittently closing inlet. So under climate change, there's no change in inlet type by the future year 2100, but there's an increase in the inlet stability level. This brings me to the conclusion. Here we present the approach to model climate change impacts on intermittently closing inlets with the ensemble modeling framework, the use of numerical process-based model. Here we use model Delft with the snapshot modeling approach. This approach was developed for both data poor and data rich environments. I also would like to mention here that this approach is not only applied to study ICIs intermittently closing inlet system, but also to study other small tidal inlet types. To touch on the results, this study shows that climate change different variations in wave conditions are the main contributor to the impacts of climate change on inlet stability. Sea level rise and changes in river flow only play secondary role. If you're interested for more details, we would like to invite you to visit our publication as listed here. Thank you very much.